if we have too high a velocity gradient coming out of that diffuser, then what would happen? Okay, so we have these green guys coming out, and if the velocity gradient is too great, what will happen to those green flocks? They'll be sheared, they'll become smaller, and then they'll turn into the red guys that are settled too slowly and end up not being caught by the plate settlers. So this is one hypothesized failure mode for this kind of a flock filter system and the Albert design, that if the velocity gradient coming out of the diffusers is too high, it'll cause us a problem. And then the very good question is, well, wait, Monroe, if you're saying that the green flocks can be broken up because the velocity gradient is too high, isn't that jet also right there? The jet is right there in the tank, in the bottom of the tank. The jet is right over here, where it goes around the corner, around the jet reverser, and then it's shooting up right here. And that's where there's lots of energy dissipation. There are blue flocks there too. Won't the blue flocks be broken up? So I went on a trike ride this weekend. It was beautiful on Sunday. And as I was taking my trike ride, I was pondering this question, trying to figure out what is going on here. And so the first thing that you should notice is that Monroe doesn't really know what's going on here either. And so you should be skeptical of everything I'm about to say. Like, you always are skeptical when you're listening to someone, right? But this is what I've done. I've gone back and looked at some of the data that we have from performance of a system where we were slowly increasing the velocity of the jet, and hence the velocity gradient in the jet, and looking at what actually fails. And the signal that we pick up first from failure is too many flocks or particles coming out from the settled water, going right through the plate settlers. That's what we see first. And then later, at even much higher energy dissipation rates or velocity gradients in that jet, we see another failure, or another indication of a problem. We see that the concentration of flocks or particles in the supernatant below the plate settlers and above the flock filter, that concentration starts to go up. So can you tell me what would be happening inside this system that would make the concentration in this region where all the vertical arrows are here, where it's above the flock filter and below the plate settlers, why would that concentration go up? And do you remember what the concentration of particles is in this region? It's the same as something else. Anybody remember? What's the concentration of flocks coming out of the flock filter? Here's the hint. In the pipe coming from the filter are green ones and red ones. And the green ones go right up through the flock filter because they don't settle fast enough, and they just keep on going up to the plate settlers. And they're too big to be picked up inside the blue flocks. And the red ones, there aren't many of them because your flocculator was pretty good. And so there actually aren't many flocks that are too small to be captured by the plate settlers. So that means that the concentration of the green guys, the green flocks coming out of the flock filter, is almost the same, or the turbidity that's caused by them is almost the same as the turbidity of the raw water going into your plant, because almost all the particles are in green flocks that are going right up through the flock filter. Okay, so now we have the next mystery. Why would the concentration of flocks increase in that zone? when you have a high energy dissipation rate in the jet, a really high energy dissipation rate in the jet. Anybody want to take a guess? We're converting one size particle to another size particle. What are we converting? If we convert green to red, what happens? Not much, because the red ones mostly are, well, okay, some of the red ones are caught in the flock filter, but eventually you would see that as really bad performance, because we would be having more red guys come in. But the blue guys, if we take a blue guy and we break it and turn it into a green one, that will increase the concentration of small flocks that can settle. And so they will be going up through this supernatant. So there is evidence at really high energy dissipation rates that the jet at the bottom of the flock filter breaks up blue flocks and turns them into flocks that get caught by the plate settlers. But the other evidence is that before that even happens, we see failure. We see an increase in settled water turbidity at a lower velocity gradient. And that's because we're turning green ones into red ones. So apparently turning green ones into red ones happens first. So that's the failure mode that we have to watch out for. So those were my reflections. Actually, some of those were my reflections on the trike ride, and then some of them were actually going back and looking at the data and seeing which thing was failing first. So that was just FYI, part of my reflections on the question that I had from one of you last week. And I want to go now to, all right, so now to the beginning of what I was really supposed to talk about today. So there's another failure mode related to plate settlers that is pretty important. And it's called flock rollup. And I'm hoping my animation works right. So this is what we want to have happen. We want a flock to go up and then slide or roll back down the plate. Looks great. And then what happens if we make these plates get closer and closer and keep the same velocity going between these plates? And we get this. Wasn't that so exciting? You weren't expecting that. And because it was animated, it must be true, right? So what happened to the poor second flock that thought it had done a good job? It had nicely settled down and made contact with the lower plate. It should have rolled down the plate, but instead it kept right on going up. Can you see what's happening? Anybody want to comment? What's our failure mode? Oh, and I'm guiding you. I've drawn a velocity profile. The velocity between these plates, it is actually laminar flow between these plates, which means you get this lovely parabolic velocity distribution. So what does it tell you about the velocity close to the plate, but not actually on the plate? The velocity on the plate is, anybody remember? What's the velocity right on the plate? Yeah, good, it's 0, it's a solid 0. But if you're just a little bit away from the plate, what happens with these two different systems? Or more to the point, what's the velocity at the center of the flock in both of these cases? The average velocity is actually the same in these two systems. But the velocity that the flock is experiencing close to the wall is higher in the narrow case, because the velocity gradient has to be steeper, because you still have to have the same parabola squished into that smaller space. The middle of the parabola has to have the same magnitude. So that means that the velocity gradient is steeper. And that means that you go a short distance away from the wall and you hit a higher velocity. And if that, can you see what the failure mode is? If the velocity at the center of the flock is higher than the velocity at which the flock would want to slide down that incline based on gravity, then that flock's going to go up instead of down. So I'm not making this up. This is actually a real failure mode in plate settlers. And this is what determines how closely you can space plate settlers and have it work. And I'll explain why you might want to get them really close together in just a little bit. So the connection to sustainability is we can actually make a cheaper plant if we can space these plate settlers closer together. And I'll show you that eventually. So here's the solution scheme. We find the velocity gradient next to the plate based on the fact that it's the parabolic velocity distribution. We find the fluid velocity at the center of the flock based on the diameter of the flock and its radius. And then we find the terminal velocity of the flock down the plate for the case of zero velocity fluid. So this is the flock terminal velocity would have been G times sine alpha. And we set the velocity of the center of the flock equal to the terminal velocity of the flock sliding down. And when those two are equal, that means that the flock will just hang out there and won't go up or down. So that's like right at the failure mode. And we can use that to figure out how closely we can place the plates. So this is a plot showing different plate spacing, minimum plate settler spacing in millimeters. And it's a function of temperature. Temperature ends up being like so important in the design of water treatment plants. And of course you have to design for whatever the critical temperature is. And for sedimentation and flocculation, the critical temperature is the coldest one you're going to have to deal with. So what do I see? So look, you can look at the equation and see some things. For example, S min is proportional to the vertical velocity between the plates. That means that if you have a higher upflow velocity entering the plates, you have to use a larger spacing. So Agua Clara uses a lower upflow velocity than some of the conventional designs. And that means that we should be able to get away with a closer spacing of the plates as well. Another thing to point out is that a really important factor is this density of water divided by the density of the core particle that makes up the flock. Like it could be a clay particle or it could be some dissolved organic material that is become particulate, minus the density of water. So for flocks where the core particle is not very dense, that density of core particle minus density of water can actually approach zero. Those two densities can get very close together. And if those densities get very close together, the equation blows up. And it says you're going to need really widely spaced plates so that you don't have this problem. And that is kind of one of the big areas of unknown for us. We know that if you have flocks that are made primarily out of dissolved organic matter, that they are super challenging to capture. And that's the reason that the density of the core particle is very close to the density of water. And so they will happily just slide up the plates, even if you do get them to land on the plates. So if the density of the core particle is at least 1,150 kilograms per meter cubed, the red line, then it looks like we could get away with 20 centimeter plate spacing and we'd be fine even for the coldest temperatures. The problem is that we don't actually know like what the density of the core particle is that is our critical case. And this is where there needs to be more work to characterize what the core particle density is that you're trying to remove as a function of the raw water quality. More work to be done. So anyway, we use 2.5 centimeter spacing. That's the plant that I have here in the middle of the slide. Spacing has a big influence on how deep the sedimentation tank has to be, so that the tank gets deeper as the plate settler spacing increases. And do you see why that's true? If I increase the plate settler spacing, in the plate settler equation, the length of the plate settler divided by the spacing is an important dimensionless parameter. So if I increase S, I have to also increase L to get the same thing out of it. So you can see that in the drawings, as you go from 1 centimeter spacing to 2.5 to 5 centimeter spacing, the plate settlers get longer and longer. The other thing that's happening is in each of these designs, the total area of plate settlers is actually very close to the same. So in order to get all that area in there, we have to have longer plates when they're further apart. And so conventional designs, conventional plate settlers use 5 centimeter spacing. We've dropped that to 2.5 to make a more compact plant, but we're not going to go to 1 centimeter because the analysis suggests that we would run into failure if we went to 1 centimeter, although it would be a cute little design, but it wouldn't work. Cute, but okay. Okay, that's my conclusions. We're trying to catch flocks that have sedimentation velocities greater than the settle capture velocity. And that is about plate area, the plan view area. And then the spacing determines whether flocks are going to keep on rolling up or whether they're going to do what we want, which is slide back down and turn into blue flocks. So some confusion. We don't yet have a basis for choosing a settle capture velocity based on overall plant performance. Our settle capture velocity is something that we pulled out of the air. We pulled it from a website, but it wasn't based on first principles or physics. Same thing I would say for our spacing. We knew that convention was 5 and we decided we were going to go less, and we went to 2.5, but that was also a number pulled out of the air. It's possible that 2 would be fine. It's possible that 3 would work better. Things that we don't know for sure.